The paper we're diving into today is Dark Matter as the Difference of Inertial and Gravitational Mass by David Lush.
Yeah, and wow, what a title, right? Dark matter as the difference of inertial and gravitational mass. It already hints this isn't your usual let's find a weird new particle approach.
Right. So the core problem Lush is addressing is the whole dark matter mystery. You know, galaxies spin way too fast to be held together by just the visible stuff: stars, gas, dust. For decades, we've wondered, what's this invisible, dark matter giving them their extra gravitational glue?
But here, Lush comes at it from a totally different angle. Instead of inventing new matter, he's basically saying, well, maybe the laws we use to add up mass, inertial versus gravitational mass, need a rethink. That's pretty wild, because, in physics class, weren't we taught those two are always equal?
Exactly, and that's key. So he's questioning something fundamental. Lush builds his argument by combining two unconventional theories. One is Osiak's tweak on special relativity, and the other is the Harari-Shupe model, which says that even the building blocks of matter, quarks and leptons, are made of even tinier things called preons.
Yeah, that preon thing is wild. In the Harari-Shupe model, every elementary particle is basically a combo of just a few types of preons and antipreons. So, at that level, matter and antimatter are thoroughly mixed together, which is not what we usually think.
Right. So, if you take that and then bring in Osiak's alternative relativity, which, among other things, apparently allows different ways of adding up energy and mass for composite systems, suddenly you can get situations where a lump of matter's gravitational mass, the amount it pulls gravitationally, is different from its inertial mass, the amount it resists being pushed.
Okay, so you're saying that in this hybrid theory, a hunk of matter might weigh more gravitationally than it weighs when you shake it or put it on a scale?
Exactly. And that might sound bizarre, but Lush argues that we only measure mass via inertia, or the weight in the local gravitational field. But if these quantities diverge because of this preon-antipreon mix, we could be underestimating the true gravitational mass of, say, a whole galaxy.
So under this model, when astronomers measure the mass of galaxies using stars' orbits, the numbers seem too low. But that's because they've been using the wrong version of mass all along?
That's the idea. If we've been equating inertial and gravitational mass, but in reality gravitational mass is higher, then the so-called missing mass, the dark matter, is just this difference. It's not made of exotic new particles, it's baked into the fabric of what we already have.
One thing that fascinated me was that Lush even tries to estimate the ratio of dark to visible matter by tallying up preons and antipreons in a typical atom, like deuterium, and he ends up getting numbers that aren't far off the dark to visible matter ratios we see in observations, like 6:1.
It's definitely a hand-wavy calculation. He even admits that. But the fact that it lands in the same ballpark is, at the very least, pretty suggestive. But of course, these models aren't mainstream.
No, but it kind of gives you a different feel for what academic research means, right? Like, it's not that he's claiming absolute truth, it's more, here's a framework, here's a way to see familiar problems from a new angle, and if it sparks an experiment or a new analysis, then awesome.
True. And he does mention possible ways to test it. Like, if you could somehow make highly precise gravitational constant measurements with test masses of radically different composition, you might see tiny differences. That would give a clue.
That reminds me of, sort of like the early days of atomic models, when you know you're missing something, but you're not sure where the fudge factor is yet.
Or like, when people first suggested the neutrino to explain missing energy in beta decay. At the time, maybe it seemed desperate. Now it's basic knowledge.
I think I read somewhere that most dark matter searches have been looking for new particles, and, well, nothing so far. This paper offers a reality check. Maybe we're barking up the wrong tree?
Or at least, maybe we shouldn't rule out wild alternatives.